Thank you very much. It's very nice. Thanks also, Josh, for inviting me here. Thank you also for not asking the title very much in advance, so I could make it up just a few minutes ago and try to connect somehow what I want to say with what you are talking about. So you are talking about intelligent music production, and I want to talk about intelligent creation of music. So it's really pretty much the same thing, and I was trying to find a stronger relation between these two things. And from my viewpoint, I'm older than most of you, so I'm more, as you can imagine, interested in music like it was before, where harmony, melody, and things like that matter actually much more than sound. And today, I recognize it's clearly the opposite. And to the point that, from my viewpoint, music production used to be about transforming sounds, applying effects and stuff like that. And I think today music production is more about actually creating sounds, not necessarily from scratch, although there are more and more synthesizers, plugins in the workstations to actually create sounds. But even what we saw this morning is, I think, more to do with creation and invention of sounds than strictly processing or transformation. So in that respect, I want to talk a little bit about the current state of, some highlights of the current research that we are doing, and there is an increasing number of people actually in the world now really getting seriously interested in how AI, machine learning, and all that can be used or developed to actually create or generate a new music or interesting music. So I will just give some examples of this. And as a background, as you know, AI and machine learning, if you go to actually pretty much any conference in any domain, people talk only about deep learning. I mean, of course, computer science conferences. And it's interesting to see that AI and deep learning and all that has been eating up the world in pretty much all the domains of entertainment, except music. So there are very interesting results in script generation, movie generation, images, actually what they call style transfer, which I will talk about, for images, even for videos. It's really very, very impressive. But if you look at it, there is still a big thing in music. And the reason why I think is that somehow music is more difficult than all that. And raises a lot of problems that I want to mention. But also another goal of this talk is also to show you some technologies or frameworks we use in music generation that could possibly be used also for, let's say, intelligent music production and automatic mixing. So basically, the world we are in currently concerning generative music and machine learning is you have a set of examples. You call this a training set or whatever. You try to infer some kind of model, some kind of statistical model, and then you can sample or can generate from that model new things. And actually doing this is actually very, very easy. With a Markov model is pretty much straightforward. Even with a neural network is very easy today. Even with a deep network, it's very easy. I mean, you can do it in a few lines of Python or all these languages. And even you can do an audio now. A few days ago, maybe you have heard of that. You can also actually synthesize audio that way. What is more interesting and, of course, more difficult is when you want to add some constraints. You want to say, okay, I don't just want any sample from this model, but I want something that ends in C major. I want these two notes to be different, and I want a sound that is more like and less like that, and so forth. So all these things, we call them constraints, ways that you want to direct the generation. And so a lot of our work in the last couple of years or so has been to identify techniques that can solve some of these problems, and we have shown that some of them are actually very hard. Some of them are polynomial, some of them are NP and P, depends. So it's the situation is pretty complex. And there are lots of results now about that. And this is very interesting because when you have a type of constraint that you can impose to a statistical model, then you can use this very, very productively to do many, many different things, not only music, but also, again, maybe production and other things. So this is just a picture extracted from a book that will come out in 2-3 months about all the kinds of constraints and the complexity of the algorithms when you try to impose them. I want to say something very simple right away. If you take a deep network, an LSTM, and you want to impose what we call a unary constraint somewhere, well, you cannot do it. Okay? So even very simple constraints are actually very hard to enforce, let's say with guarantees. So the problem of, again, building a statistical model is now pretty much understood, but the problem of generating under constraints is much harder. And I want to give some examples by taking this experiment we did actually last year, where the ERC asked me to reorchestrate the European anthem. Of course, well, it used to be your anthem. Sorry. Anyway, I am in France. Well, actually, SONY CSL is English. SONY Europe is in England. So. And in such a way that the melody of Ode to Joy could be recognizable, and also the style of the reorchestration should be recognizable. And there was another constraint. I removed the picture, but this had to be played in a big room where many people would have a drink, so they would not listen very carefully. So the sound, the production was also extremely important, so that all these things would be recognizable with a very, very loose attention, that could be guaranteed. So the result is on the web. You can check the video. We had a lot of success with this. Very, very nice, a lot of stuff. But I will take a few examples from this just to illustrate what I want to say. So this is the starting point, the lead sheet of Ode to Joy, the melody, and some chord labels on top of it. This lead sheet, I did it. Of course, Beethoven didn't write this lead sheet like that, but it's more or less what you can you could do if you have a reasonable ear, let's say. And so this is a target structure you want to fit into and take some styles and fill in the thing. And the first thing we had to do, the one out of the 7 styles that we generated, was Bach. It was interesting to have Bach chorales in the style of Beethoven, of course. It's a bit anachronic, it's interesting. And Bach chorales are actually very, very difficult to model for many reasons. So what is a Bach chorale? It's something like that. This is a real one. So you have 4 voices in that case. And you have lots of things going on in here that I will not review. But basically, the idea was to take this, extract a kind of texture from this set of chorales and reapply it to Ode to Joy. And we found out that actually a very interesting model to do this. This is an exercise that has been done a lot of time in computer music, by the way, but never with really very successfully, was to shift from the old kinds of model we used to use in that community, basically Markov model, to more powerful models used in statistical physics called max entropy models, which are really able to capture long-term correlations between events, which Markov models cannot do by definition. You are limited to some context, and the context is very small because you don't have many data. And so when you have a chorale like this, you have lots of interaction that occur between notes that are not necessarily very close to each other, and also between notes vertically and diagonally, and so all this it's very hard to do with the Markov model. It's really very hard. So we got interested in those models, and these are called also energy model, if you want, or exponential family models, because the probability distribution is actually represented by an exponential of the Hamiltonian, which represents somehow the energy of the system. And the energy itself can be decomposed as a set of interaction contributions, which are all binary. And this is why estimating these parameters is not easy but feasible. Otherwise, it would not be. And nowadays, with the progress in gradient search and all that, you can actually estimate these things pretty easily, a few hours, a few days, depends. And so what you get with this is a very interesting way to do a Bach chorale generation. So I would this is a video that exemplifies the idea, but you take, so the top soprano is Ode to Joy, and this is a random solution, all completely random, but then there will be some iterations, and then progressively the system will do a Monte Carlo search and try to get a probable, let's say, to optimize the probability of of the system and converges very quickly in a few milliseconds, actually, and you will see progressively, sorry, a bit better, some wrong notes. And this one is perfect, so there is no wrong note in that. And there is no knowledge. I mean, everything is completely automatic, of course. Oh, sorry, I wanted to just do it again just to show something. Sorry. So here, just in passing, what we have shown is that there are the red stuff, white, and green, and this one is the one which works well. And the white things, the white chords are chords that were already in the training set, that were just reused, copied if you want. The green ones were not in the training set, but they were in another Bach chorale, and the red ones were completely invented from scratch. And so what's really interesting with those systems, when you have a very good estimation of the probability distribution, that you can actually create new things in the style, and they can actually measure how much you can create, which is something that we can show that you cannot do with other models like Markov models. So these models are not only better, but they're also even interesting to create new things in the style. There is a lot of work currently in the lab about extending these models to handle full polyphony. Here I cheated a little bit, maybe some of you noticed, but you have vertical homorhythmic polyphony. So you have one only chord, succeeding chord. You don't have like a counterpoint movements. So we work quite a lot with the guy there, these two guys, to extend this to full polyphony, and it works extremely well. So it's quite impressive. So there are a few examples here. So this is a simple, I think, 3-voice Bach random walk without any constraints. This is Palestrina. There is no repetition, there is no plagiarism. It's very, very efficient. And of course, so in the papers that we're going to write, we are going to measure exactly the degree of plagiarism. This would be very impressive if I played an original Mozart piece, but most of you would not notice it's an original, there is nothing new. Here, what's interesting is that there is no plagiarism, and the model is really able to capture a lot of complex interaction going on. So the ode to joy exercise, we could do that way. The paper that's going to come out in ACM TIST is going to describe all the work done actually mostly by Emmanuel about the production, how to make this actually sound nice in a big room, and actually there's a lot of work there, which I think is very interesting, which we cannot model currently, we cannot automate completely. And just a few examples about the recent model extensions of these models, so with hidden layers, where we use LSTMs combined in a very specific way to capture all this and to produce full polyphony with multi-voice and enable unary constraints, which you cannot do with LSTM. So this is, for instance, your. The harmony is not given, just the soprano. And so you can hear all the voice movements. So it's in statistical physics. They say that the system in a good region of the just before the phase transition. So there are lots of very interesting things happening. And what is kind of magical is that you don't have to do anything. It just works like that without tweaking or cheating or anything. I don't have the time, but these models are also very interesting. We have been using them to model expressiveness or expressivity, I don't know. So, the problem, how you go from a strict score, which is quantized, to something that sounds human, like a straight Donali. This is just the score played with a metronome. and when it's Jaco, of course. Lots of stuff happens concerning onset deviations, amplitude, modulation, all that. And so the problem is, how can you model, how can you capture these onset deviations, these style of expression, capture it in a statistical model and reapply it to something else? And we have shown that these models are actually very good to do that. There is an online test going on, actually, where we compare a human performance of Donnelly, this thing, with a random model. You can hear it's random because there is no correlation between the onsets, especially long term. Well, there is no even short-term correlation, but with those models, you can capture and reapply those correlations on completely new things. Of course, this is generated with a training set which does not include the results, obviously. Okay, so much for polyphony and these things. I want to mention jazz a little bit because jazz raises a completely different kind of problem. So basically, you give a lead sheet to a jazz musician, a jazz pianist. It will transform it into ways that are very different from what Bach is going to do. Bach is going to follow strictly the soprano. You know, the jazz guy is going to add a lot of stuff in between, you know, to make it sound more interesting or strange, and always trying to make you, recognize the melody. But there's lots of more freedom, and so in that respect, it's much harder to model. So we have done some work with Markov model actually here, but with some of the techniques we have been developing. So I like to play this example for those of you who hear a bit of harmony. Maybe there are no such spaces anymore. But so this is a traditional song where you have a B-flat major chord supposed to be here by take 6, and they do this, and then they go there. So what they do is very, very. See? So when you have something written B-flat and you do this, you are really very far away from the target structure, the structure you're trying to go to. So how can you model this? So this is not really style transfer. It's really about how to get away from the target, but then coming back in smoothly and in interesting ways. So we have done some work about that. I will go very quickly. This is published, where we can, for instance, given a target, which is these two notes there, like E to D with those chords, and then you say how many notes you want to do. Well, I can give you like 2 or 3 or 8. So if it's 8, you get this. Oh, sorry, I will try with 2, 3 notes. So a jazz man will add a chromaticism here. But if he has more notes to play, he can. Okay, or. Okay. So in those cases, you have boundaries on these 2 notes, and then you give some freedom in between the E. And we have shown that you can do this with control random walks, very, very with no complexity. Once the model is built, all these solutions are created instantaneously. So it's quite interesting. Giant steps by So if you know giant steps, you probably kind of recognize it. It's somewhere in the soprano, but there are lots of fioritures done with a training set from Wagner Polyphony. So this is Ode to Joy. You can hear all the new things added on top of the soprano. Especially this cadence here, which is typical of take 6, which is not in the score, but so we can show that we can model to some extent this flexibility of jazz comping. How much time do I have? Right. So No, because, okay. So we are doing so the third style was Bossa Nova because I'm myself a bit obsessed by Bossa Nova. It's a style I like, and I know very much how to play Bossa Nova guitar. And I wanted to do something. So Bossa Nova is characterized by the fact that everything is wrong. So all the melodies, a harmony. So you ask a Brazilian guitarist to play C major, I will play something where you don't even have a C and an E and sometimes none of the triad chord, but it sounds very nice, you know. So, and the rhythm are crazy and goes everywhere, but of course there's some logic in there. So the problem is how to capture these things and in order to generate new accompaniments, Bossa Nova accompaniments. And then when we try to work on that, and this is work by the way with Mathieu somewhere there, we realized that one of the crucial difficulty was to deal with onsets. Basically in Bossa Nova, actually in all perform music, people don't play on the beat. I don't know if you have noticed this thing. So they play a little bit before, like here on the D9, an anticipation, or sometimes they play a little bit after. So all sorts of bad things happen. So if you do concatenative synthesis, either you quantize everything and it works perfectly, but you completely lose the groove, or you don't, and then you create lots of artifacts. And so we had to address this issue, and I think we got a very nice result, actually. So I will just show you. So this is a human guy here playing in sensatez. So you have to listen to the guitar only. And you can see the rhythm is kind of laid back, a bit behind the beat. And the harmonies are, you know, these things, Brazilian stuff. And sometimes it's clearly not within the bounds of the beat, okay? And so we can take this and apply it to any song. So this is blue and green, it's a jazz standard. And you can hear the anticipations, everything is reproduced in a nice way. And you can do this. But you can do this also for any kind of audio that has these properties of being not really on the beat, like guitar strumming. So this is Friends to Go, a song by Paul McCartney. This one. So but strumming, actually, if you look carefully, the guys always play a little bit before or after. So you cannot do concatenative synthesis from, let's say, a human recording. But we can do it. So this is all of me by using this. So there is no cheat. I mean, it's really pure generation. And you can see that everything is smoothly concatenated, transposed, stretched, and also anticipated on that. So this is what we got for Ode to Joy. Of course, we added a little bit of what they call production, which I used to call bass and drums. Now bass and drums is actually production. This is very interesting, by the way. Okay, so actually I really wonder what's left for music. Everything is production. So we can do all this now, pretty much. But this is a kind of, again, a style transfer. We know where we are going to. We have to stick to Ode to Joy or to whichever target. So just very quickly, we had also as a constraint to do, let's say, individual styles corresponding to individual songs, which does make any sense for a musicologist because style, by definition, concerns a lot of songs or corpus. Anyway, but so the idea was to say, let's take one song, like this song is very famous in France. I don't know here. And so you can do this. The drum there is a bug in that version. I didn't replace it. The drum is going too early. and so forth. So to do that, it was really interesting to see that the problem at here is a different problem. It's a problem of generating 3 sequences, bass, drum, and guitar, or depending on, that fits to some chord label structure, but also so that there are synchronization points every now and then. And so this synchronization problem turned out to be extremely hard. It's really more than NP, it's very hard. But we proposed a solution recently in this paper, which was shown last week in Toulouse at CP, to do that in reasonable time. So what you get is this, so it shows a little bit what's going on, but here you have Penny Lane and 5 minutes to the moon. And you see that all the chunks here are taken from the original, mapped into this, so that they are synchronized when you have a chord change. Otherwise, they are, let's say, free to go where they want. It works pretty well, but it takes a lot of time. This cannot be done in real time currently. Okay, I'm progressing. This is on the web. All this is on the web. I want to talk a little bit about lead sheets now, because this is my favorite subject. And I think this is the most difficult problem that we have in music generation. It's much harder to generate a nice lead sheet than to generate a symphony by Mozart. I know that if I say such a thing, many people will hate me, but my experience in music is really that this is a kind of true. So we have a big database of lead sheet called LSD, of course, with all the lead sheets in jazz, American songwriters, let's say the basic stuff of tonal music, tonal pop music, until, including some pop and the Beatles and stuff like that. And so I'm just going to give you some examples. So we have a tool called Flow Composer, which also we released a few weeks ago, in which you can select a style, a set of lead sheets, and then generate a lead sheet in that style, possibly adding constraints. For instance, you have an idea, you want to start a phrase and you don't know how to continue, so all this can be done with the interactive system that we are proposing. So this is just one example with Miles. I think it's 12 bars. It's a very simple example. That's it, it's 12 bars. So if you listen to it carefully, it's on the web, you can see there are lots of structure in there. There are lots of similarities between various bars, various subsequences. So all this now we can do with those techniques automatically. So this is a purely automatic generation of the lead sheet, and the rendering you hear with the piano is also automatically generated with the technique I showed for the Bossa Nova. Another example, we wanted to do something that grows for 12 bars that you can play in loop. From Miles, again, Miles Davis, without any human intervention. So this is what we got. For instance, one example. And so you can notice the only human intervention that we wanted a C7 at the end. Well, we wanted at the end a chord that resolves onto the first, so they can play it in loop. I can assure you, if you play this twice or 3 times, you cannot get this thing out of your head. It's very sticky, very, very sticky. So here what you listen to, so the score, the lead sheet is generated, and the rendering here, bass drum and some kind of guitar, is also automatic. Everything is automatic in that case. And it's, as far as I know, not produced. It's completely raw audio, and there is no mix and effects and everything. There is a video on the web that shows what you can do with all this. I just want to conclude with some examples now. So currently what we're trying to do, the goal now is not so much to prove that AI is able to generate interesting lead sheets, because it's something we are quite convinced already. But the goal is your problem. Now, as you know, a lead sheet is not enough to make it to the radio. You have to produce it. And production is actually a lot of, is more than maybe 80 or 90% of the work. So currently what we are doing is we are producing some of the songs that we have generated with our technologies so that they sound okay, so that you can put them on the radio. So we are going to announce very, very soon an album, several albums. One album will be the next Beatles album. So I can give you an extract of one song. I don't remember which one it is. It's this one or not? This one. Yeah, this one. You have to play it very, very loud. And so forth. I mean, it's real fully fledged 3-minute songs, and we will have 12 or so. And so we can do this, of course, in many different styles. There are, again, examples on the web. There will be more soon. There are things for old people like me, like the Beatles. There are things that are more modern, like this kind of thing where we are using voice synthesis. This is actually the Dean Martin's voice taken from Rio Bravo, the song. Well, you don't know this; you are too young. But so what we're trying to show that all these techniques can generate lead sheets, can generate actually also I don't know how to say maquette. I mean, very rough realizations or renderings with lots of different styles of accompaniment, also multi-track. Of course, from that, so this is okay now. We can do it. Now the next step is, of course, how to go from these things to the thing that is played on the radio. And so my conclusion is actually the subject of this workshop, of these workshops, is really how can you go now for the next step. And so we have a project which I didn't talk about, and if you want to talk about that, Emmanuel there is working on that, where we try now, based on some of the examples we have of real mix, we try to build an automatic mixer that, let's say, approximates more or less what's going on. This is just an example of the Beatles song. So this is the human mix. It turns me on. Good day, sunshine in the back. By the way, this is not a professional sound engineer. It's just a good musician. It's not the perfect mix. It's let's say, a decent mix. And then this is what the system is doing on the right. It turns me on. Good day, sunshine in the back seat car. I wish that road. Well, it's very hard to compare them like this in a conference, but this is on the web. Please come and talk to us about that. There is an online demo with a whole pop album which has been mixed, which is an album that exists, that is for sale in France, and it has been remixed with the Automix, and you can compare. It's quite interesting. Sometimes it's really very good. There are some listening tests, and this is really the subject of this thing, and I will stop here. But I will just mention as a conclusion that, again, I think that intelligent production is well, more, let's say, as much about generation and creation than about strictly transformation. And so in that respect, it's interesting maybe to look at those techniques that are developed for generation. There are a lot of things happening currently, as you probably know very well, not only in machine learning, but there is computational creativity. There is what is called constructive machine learning, which is an area of machine learning interested in precisely developing machine learning algorithms that are able to navigate infinite space or very, very large space like the space you have when you create an object. So there are lots of things going on with very powerful models, and I think it's really the right time to look at that. And the remaining problems we have for generation of music, basically, I just pointed the two I think are most important. The first one is high-level structures. We have no idea how to generate an A-B-A. Of course, it's very easy to generate an A-B-A. You say generate an A, generate a B, and then that's it, you know. But the thing is, how can you design a system that has this idea of doing A-A-B-A or A-B-A-B or whatever? So how can you generate high-level structure that's somehow related to the content, not mapped, of course, arbitrarily, which is something we can do. This is really hard. This is very hard, and of course there are lots of attention models, and memory models and stuff like that that are interesting, but they do not solve that problem. It's probably much harder. The problem that's really interesting for us is this one. So because when you compose music, actually it's not true that you compose a lead sheet, where you have notes and stuff, and then you go to the studio and you think about sound. Obviously, it doesn't work like that. Everything is mixed together. And even if people don't play with sound when they compose, they still have the sound in their mind. And so the interaction between the rendering of the sound of the guitar, the piano, the whatever, and the score is of course very, very important. And no one is working on that today. No one. People are working on symbolic generation. Some people are working on audio production. Some people are working on audio generation. No one is working on the relation between these two things. And to me, this is the hot topic of the next topic to study. Sorry, I've been a bit long. Thank you very much.